All right, so we're going to carry on. We're going to do a kind of walkthrough of a hypothesis test. And I think I have a 7-step breakdown, 8-step breakdown here for you. And certainly at the beginning, and when we're getting used to this, we should identify, which steps are we doing. Try to do it the same way every time. If you, just like with anything else, if you get comfortable with it, you can kind of streamline it, maybe absorb some steps together. But we're going to try to keep everything very clear here. Okay, so suppose you would like to test whether a coin is fair. Not the world's most important hypothesis to test, but it's one that we can all understand, right? So we want to test whether the coin is fair. So we flip the coin 100 times, and let's say it comes up heads 72 times. So we're going to carry out a formal hypothesis test, and then we're going to state the conclusion. Okay, so what is the claim here? What is the claim? We're basically saying, um, well, maybe there is no claim yet, so nobody's claimed anything. Let's change this slightly. Suppose you'd like to test the claim that a given coin is fair. So somebody says, "Here's a quarter. It's a fair one, I promise you," and then you decide to test that. So the claim is that um, the proportion of heads in the long run is a half, is 1/2. So that's in words. That's what being fair means. So in symbols, we're saying that the proportion p equals 1/2. The proportion of heads in the long run is 1/2. Okay, step 2, we're trying to figure out what is the null and what is the alternative. So step 2 is we find this symbolic form of the negation. So if that first claim is false, if the claim is false, then how would we write that in symbols? Then, well, this one's pretty easy. We just negate it. P not equal to 0.5. If the claim is false, then P is not half. So now we can identify what is the null and what is the alternative. So the null hypothesis is the one that involves equality. So it's the first one. It's this claim, equals a half. The alternative hypothesis is the one that involves either greater than, less than, or not equal, right? Those are the 3 possibilities for an alternative, and that's what we have. So now, I want to point out something here. From the data here, it certainly looks like this is biased towards heads, right? But never mind that for a second. The alternative hypothesis is that it's just not fair. So we're on the lookout for either lots of heads or lots of tails. Either of those would tend to support the alternative. So I'm going to draw a little sketch here that we should keep in mind. So we're interested in what we'll call a two-tailed test. So we're on the lookout for we're looking for extremes in either direction. Anything that should be rare, like very many heads, or rare because it's lots of tails, both of those will be considered evidence of not fair. So that's a two-tailed. It's going to be what we call a two-tailed test. Okay, significance level. What do we choose as the significance level, which is alpha? And here we're just going to choose the default, what we usually choose, which is 5%. which is the usual definition of unlikely. Unlikely. Unless there's some other, so we do that unless told otherwise. And okay, so now we get to the calculation part. We're going to identify what's called the test statistic. So the test statistic, that's what tells us, it tells us how extreme is the observed, how extreme is the outcome that we actually observed. It tells us how extreme is the outcome that we actually observed. So in this case, the test statistic is going to be a Z statistic, and it's going to be the p hat value minus what we're going to call the p0 value divided by square root of p0 q0 divided by n. So what is this thing that we're looking at here? What this is this thing in the bottom, that is the sigma of p hat if the population proportion is actually p0. And in this case, p0 is going to be the value of the null hypothesis, a half. So in the denominator we have sigma of p hat. It's the standard deviation for p hat if the null hypothesis is true. And here I have the mean value of p hat, which is p0, if the population proportion p is p0. Maybe I should change this slightly so it has the same form. If the population proportion p is p0, which is 0.5 in this case. So what is z then? Z is therefore, this z is the number of standard deviations that the observed p hat is away from the expected value, which is p0, if assuming, I'll just call that p, expected value p, assuming that that p is the null value, the value assumed in the null hypothesis. So let's actually calculate this thing now. So what is p hat? Maybe we should go back to here and actually calculate p hat, right? So p hat is going to be x divided by n, which is 72 over 100.72. Okay, that wasn't too hard. How far away from the expected value of a half is that in terms of standard deviations? So that's going to be 0.72 minus half divided by, what is the sigma for that? It would be a half times a half divided by 100. Now, you might be asking, wait, how did I know q hat? So we're using p equals p naught, which is a half, and q is 1 minus p naught, which is also a half. Okay, so what number do we get? Let's calculate it. I haven't actually calculated it yet. 0.72 minus a half, square root of 0.5 times 0.5 divided by 100. 4.4. 4.4. That's a really large value, right? It's 4.4 sigmas away from what it should be if the null hypothesis is true. So it's probably not true. So what we do now is we say, well, okay, how likely, now I know how extreme it is, how likely is it that it would be that extreme? So we look at we know that that z should be near 0, right? And we found it way out here at 4.4. How likely is it to get something that extreme or more? So that's actually talking about this tail. The probability of getting something that extreme or more, this is the standard normal for z, would be that area. So the p-value is going to be the probability that z is at least as large as 4.4, or since, now this will be weird, it's going to sound weird, but as extreme or more extreme would also be on this side. Since we're looking for lots of heads or lots of tails, anything that's that far away from 0 in either direction is considered to be equally extreme. So greater than or equal to 4.4 or z is less than or equal to negative 4.4. This is the meaning of as extreme or more in both directions. Okay, so now we can figure out that area, right? So fortunately, then this doesn't double the work, right? This is just going to be 2 times the probability because they're the same. It'll be 2 times the probability that z is less than or equal to negative 4.4, right? It's just 2 times this thing. So I can do that in Excel. 2 times norm.s.dist, right, of negative 4.4 true. And that's going to be pretty small. Let's see what it is. Oh, I don't have it open yet. 4.4 sigmas away. 2 times norm.s.dist of negative 4.4. Cumulative true. 1.082 times 10 to the minus 5. 1.082 times 10 to the minus 5. 1.082 times 10 to the minus 5. That's really small, right? Very, very small. I mean, if we wrote it with the zeros, it would be 4 zeros, 1082. Right? 1, 2, 3, 4, 5. Yeah. So that's a very unlikely outcome. And that makes sense because getting 72 heads, it seems like that shouldn't happen. It's very unlikely. So step 7 is, this is the easy part. Is the p-value less than alpha? Because that's what we consider unlikely, right? So is 0.000182 less than 5%? Yes. So that means that getting 72 heads or more, I have to be careful because of the negative. So getting a result as extreme as 72 heads is highly unlikely. It's certainly less than alpha. So our decision is going to be, we're going to reject the null hypothesis. we're going to say this coin is not fair. Null hypothesis. And so what's our conclusion? Well, we would say we have enough evidence to say that this coin is unfair. That's our conclusion. The given sample data is adequate evidence, and now we have to phrase it in terms of the claim. Remember, the claim was that it is fair. So how do we target that? We'll say we have adequate evidence to reject the claim that the coin is fair. That the coin is fair, which is to say that we think it is unfair. But think of it like, okay, so we're done. I'm just going to say a couple more things. Think of it like somebody comes to you, I have this coin, I think it's fair. Can you please help me with, I think it's fair, but can you help me test that? And you, at the end, you say, okay, it's not fair. Your claim is false. And then you just we just leave it at that. So we state our reply in the same form as what the question was. The question was, I think this is fair, and we say, no, it's not. It's not. Now, maybe that sounds a little too obvious right in this case, but in other cases, it can be a little confusing. Like, how do you reply in the same terms of the original claim? Well, we'll see some examples of that. Okay, so that 8-step process, that is a hypothesis test for a population parameter. And you can see it involves pretty much all the elements of the course so far. It involves sample data and probability theory and the test statistics, z-score. It involves using our Excel functions and then the careful interpretation at the end. So this is kind of you could say this is the capstone or the keystone of the course. Everything was included. Everything in the course is included in order for us to be able to carry out this kind of analysis. Okay, so I think we have another page or so, and then we're going to, yeah, okay, so now this is just a table that I copied from the book. We just did a case with the population proportion P, and the test statistic we used was this one. I wrote it a little differently. I wrote it as P hat minus P0, P0 Q0 over N. That's the same thing. We'll also do ones with mean, and then it becomes the test statistic is T, and it follows a T distribution. And that's in the usual case where we don't know sigma. Sometimes, if you do know sigma, which is very rare, it would involve Z. And then this last one, we're not going to do in this course. It is the testing a hypothesis about sigma squared. And in that case, it follows what's called the chi-squared distribution. But we can't do everything. Distribution. Okay, so if you hear about a chi-squared distribution, it's probably somebody trying to say something about the variance. And you'll have to look that one up in a textbook. Okay, so we did touch on this, the one-tailed versus two-tailed. If the alternative hypothesis is, let's say, P greater than, let's say a half, or P is, oops, it says alternative. I should have said alternative 1, P less than a half, then we use a one-tailed test. So if I say I think this coin is biased in favor of heads, then this is my claim here. I think it's biased in favor of heads. Then I'm not looking for many tails, I'm only looking for many heads. So what counts as extreme is only things to the right. Extreme only includes large values of p. Only includes the right tail. And whereas if I'm looking for this coin is biased towards fewer heads, then I'm looking for evidence in the left tail. So I include only the left tail. And so that affects when I calculate the p-value, I only use one tail. So in both these cases, you calculate the p-value using only one tail, using only the appropriate tail, either the left one or the right one, the appropriate single tail. On the other hand, if it's like the one we just did, if the alternative hypothesis is p does not equal something, then we're looking in both directions. So we use the two-tailed test. So we're allowing for both kinds of extreme. So let's say that's our test statistic z minus z. Then we calculate the p-value using both tails. Okay. Lots to remember. I think we have, yeah. So we're not going to do a full run through with the hypothesis test, but just the sort of preliminary steps here. Let's say we're investigating the mean height of men. A formal hypothesis test is to be conducted using the claim, that's the keyword, claim that the mean height of men is equal to 174.1. So the claim is that the mean for men is equal to 174.1. What is the negation of that? So step one is always write down the claim. Step two is what is the negation of the claim? The negation here is the logical negation, in other words, is that it's not equal to 174.1. And now we can decide which one is the null and which one is the alternative. So the null hypothesis is always the one that involves equality. So it's equal. The alternative is the other one that involves less than, greater than, or not equal. Okay. How is it denoted? It's denoted like that. I guess I just did this. What is the alternative hypothesis? Just did it there. What are the possible conclusions that can be made about the null hypothesis? Okay, this is kind of new. So we can do two things. We can either reject the null hypothesis. So I think that's probably clear enough. It means we don't believe it's true. Men's heights average, the average of men's heights isn't 174.1. So we, in other words, we conclude that it is false, is likely false. But the other, now you'll be surprised here, the other conclusion is not that, it's not that we conclude that it's likely true. It's something in between in a sense. It's that we fail to reject. We fail to reject the null hypothesis. It's kind of like saying, well, do you like me or do you dislike me? And you say, well, I don't dislike you, right? It's not the same thing as saying I like you. It's so we're not rejecting the null hypothesis. We're not accepting it. We're just failing to reject it. So it's like we don't dislike it. We fail to reject the null hypothesis, and what that means is we continue um, to uh, to to we continue with it. We continue to maintain the null hypothesis, but we're still we're still open to evidence against it. Let's keep it like this. It remains our default. The null hypothesis remains our default assumption, but we're still open to evidence that contradicts it. It remains our default hypothesis, but we are still we still accept that it might be contradicted in the future, but we acknowledge that it might be. How do you spell acknowledge? That's a tough one. Acknowledge that future evidence may contradict it. And that's also like in law, you know, you say, well, you're innocent until proven guilty, and let's say you have a trial and it says, well, we can't convict you, the evidence wasn't strong enough. I guess maybe in real law, it's not they can't bring you back and say, no, we found more evidence, you're going to go on trial again. But that's how it is in science, right? You have a theory and you test the theory with an experiment and you say, well, it passed the experiment, but maybe in the future we'll do another experiment and it won't pass that experiment, and then we'll have to reject the theory. So the null hypothesis is on trial for life, so to speak. You know, we never just say, oh, it's true. It's always trying to prove itself. So we don't accept it, we just fail to reject it. Fail to reject. Once you start using that phrase correctly, then you won't sound like a regular person anymore, and you'll know that you've been learning statistics. Okay, so last one. Is it possible to conclude that there is sufficient evidence to support the claim that the mean height of men is equal to 174.1? So in other words, is it possible to conclude that is it possible to conclude that the evidence supports the null hypothesis? Well, that's exactly what I was just talking about. So is it possible to conclude that we should accept the null hypothesis? No, we don't ever accept the null hypothesis. We just let it live another day, and then maybe tomorrow we'll reject it. And why are we so harsh or so critical about it? There's a good reason. Let me just see. Is it possible to conclude that evidence supports the null hypothesis? No. We never conclude with accepting the null hypothesis. We only fail to reject it. Okay, and the reason for that is that the null hypothesis is always a specific equals. Let me say it again. The null hypothesis always asserts a specific equality. It's saying mu equals 174.1. it's not saying, but that's so specific. How could we ever prove that the mean is exactly 174.1? Maybe it's 174.11.11. Maybe it's 174.10001. Essentially, the null hypothesis is too specific for us to ever prove that it's exactly right. It's kind of like when we talked about probability. Could you prove that a coin has exactly a 50% chance of being heads? No, because even if you got, let's say, exactly 500,000 heads out of 1,000,000 flips, that's still consistent with the probability being slightly different than a half. So there's no evidence that could ever persuade you beyond a doubt that it's exactly that value. It's too specific. Okay, so let me try to summarize what I just said there. No evidence could count as direct support for the the exact equality that's asserted by the null hypothesis. In other words, all evidence would be consistent with slightly different values than the one asserted by the null hypothesis. All evidence would be consistent with the parameter being slightly different. Different than the value asserted by the null hypothesis. So if you need to try to remember something simple, we'd say H0 is too specific. It's too specific to ever be proven, whatever that means, right? It's too specific to ever be proven. Whereas the alternative hypothesis is not that specific. It's just saying this coin is not fair. So we can prove that. We can prove that it's probably not fair, but we can't prove that it's probably exactly fair. Maybe it's not exactly fair. Maybe it's just close to being fair. Okay, I hope that sinks in for you. So all of that is to support this, that we only have two options. We reject it or we fail to reject the null. We never accept it. Okay, eternal skepticism. Okay, so the last part is going to be on what's called type 1 and type 2 errors. And we're going to leave that for the last video. So I'll see you then.